In this video, I'm going to derive for you both the magnitude and the direction of the centripetal acceleration. Let's consider an object moving from point A to point B on the edge of a circle of radius r. Acceleration is a change in velocity, and that's a magnitude and a direction, or both, where we always say acceleration is a vector, which we can find by looking at the velocity at points A and B and taking the difference. The velocity for an object that's moving around a circle is tangent to the circle at each point. So if we're representing the velocity with a vector, we would represent it this way at point A and point B. Consider an object moving at constant speed but in a circular path. We want to know the magnitude and direction of the acceleration responsible for curving its path. The velocity is tangent to the path. If you take the difference in the velocities, you'll get a new vector, delta v. We want to know the direction of this new vector, delta v. We'll eventually find its magnitude also. The instantaneous acceleration is found by taking the limit of the expression for acceleration where delta t approaches 0. In the diagram above, that means that points A and B would be quite close together, a lot closer than I can draw in here. And if that is true, those vectors are very nearly parallel. On the next slide, I'm going to remind you how we add and subtract vectors. So just keep in mind, in an exaggerated view, they look like this, but we're really thinking in the limit where delta t goes to 0, so we're really drawing point B back up near to point A, so these vectors will be quite close to being parallel. I'll show you how to add vectors together and then how to take a vector difference, such as we have here when we are doing VB minus VA and thinking about our resultant vector, delta V, and where it points with respect to this circle. When we add two vectors together, such as vector v1 and v2 as drawn here, we add them so that we basically pick up one of the vectors and drag it over to the other vector. I'm trying to redraw v2 over here. And our resultant vector, I'm going to draw starting from v1 and extending up to v2. That's pretty sloppy. It should be a straight line. That's our resultant vector, r. When we subtract vectors, we flip them over. So vector subtraction looks more like this. If we are taking, instead of v1 plus v2, let's suppose that we did v1 minus v2. In my example here, we'd preserve v1, and then we would flip over v2. So v2 is pointing up over here. We'd flip it over and it points down here. So the resultant vector would be from where v1 begins, pointing where the subtracted result goes, and so the resultant vector of subtracting v2 from v1 points there. We're going to apply this now to our situation with our circle where we are subtracting VB minus VA on the next slide. Remember that our particle is moving at constant velocity, so the length of VB and VA are intended to be the same. If we're subtracting VA from VB, then we're going to add its inverse, sort of looking like this. Okay, highly exaggerated, and these points are meant to be really close together, so these lines would be basically parallel to one another. They don't look at all parallel in the diagram I'm drawing here, obviously. The subtraction of this is going to result in a vector that we said would point connecting these two. Alright, but what happens, we want to know, if these two lines VA and VB are very nearly parallel as opposed to how I've drawn here? Where would this vector point when we do subtract these vectors? In the limit that delta t approaches 0, when these points A and B are very close to one another, VB is nearly parallel to VA, and so we get something more like this, where VB would point like so, VB would point like this, VA would point back like this as we're subtracting it, and the difference, delta V, then points perpendicular to both of them. A line pointing perpendicular to a tangent points along the radius of the circle. So delta V points along the radius. It's inwardly directed, and that's what we always say about centripetal acceleration. It's inwardly directed. Now let's determine the magnitude of this acceleration. Acceleration equals delta V over delta t. We said that before. So we need to figure out what delta V is in terms of known parameters like V and R. So let's look at this diagram and this diagram, the one that I just made with the velocity vectors. And remember that V is a constant speed, so those lines have equal lengths. In the limit that delta t approaches 0, where the points are very close together on the circle, then we can make two similar triangles. Looking at the angle theta in the circle, it turns out that angle theta is also over here in this small triangle with the velocity vectors. And so what we can say, if we go ahead and consider that this arc length is actually sort of a straight line when the points are together, and let's call that L, is that delta V here is to side V as L is to R. This only works in the limit where delta t approaches 0. It's an approximation. So if that's the case, we're going to write that out as delta V over V is approximately equal to L over R, which means that delta V is approximately equal to V times L over R. Okay, let's plug this into our expression for acceleration right over here, and on the next slide, see what we get. We have that A equals delta V over delta t. Putting in what we just said, now we have A equals V times L over R times delta t, again because we plugged in delta V is approximately equal to V L over R. That's where we made that substitution right in here. And now we can consider that we know something else. L is just a distance, delta t is just a time, and we know that it's moving at a constant speed. V is distance over time. So really, this is just V in here. So then we can rewrite this as A equals V squared over R, and that is the magnitude of centripetal acceleration. So centripetal acceleration points toward the middle of the circle, and it has a strength of v squared over r, so centripetal force is mass times that centripetal acceleration, mv squared over r.